Now that we know what orbitals are like, we can talk a little bit more about how they exist in atoms. You might have noticed that the orbitals have these graphs of the psi function, where some of them have their little peak a little closer, like here's maybe a 1s to the origin, than some of the other ones. So we saw a couple of pictures of those. And this is 100% true. It means that electrons in the 1s orbital of an atom are closer to the nucleus than the electron in the 2s orbital of that atom. So if we have a hydrogen which has one electron, there's our nucleus. We have hydrogen. Remember a long time ago we talked about its isotope notation. So hydrogen has one proton and one electron. The proton is the nucleus. The electron then, in its ground state, that's its lowest energy state, the electron would be in the 1s orbital. If it gets excited, then it goes to a higher orbital, higher energy orbital. And if it relaxes, then it goes from a higher to a lower energy orbital. So let's actually take a minute now and get back to why the Balmer-Rydberg equation and the Bohr model only worked for hydrogen. So we've talked about several different orbitals here, and I'm talking about orbital energy. And it turns out that when you have one electron, then all of the orbitals in each shell have the same energy. So we have an n equals 1 shell, and that has a 1s orbital. And we have an n equals 2 shell, and that has 2s, but it also has 2p. And if you have one electron, these are at the same energy, but only if we only have one electron. And the n equals 3, these are not evenly spaced. I'm just doing it to make it easier to show. So if we have n equals 3, that would contain the 3s, the 3p, and the 3d, and all of them are the same energy if you have one electron. Okay? And this continues up for however many shells you have. But as soon as you add a second electron or more than that, so even if we add one more electron, the energy levels no longer are the same. In a shell. Instead, they split the subshells. So remember, subshells are the different types of orbitals, the different shapes. The s orbital and the p orbital, those are subshells. So if we are looking at those now, as soon as we have more than one electron, now our 1s orbital is lowest, and then our 2s orbital is the next, and then a little bit higher than that are the 2p orbitals, and then 3s, and then 3p, and then 4s, but now we do 3d, and so on and so forth, all the way up and higher. These are also not evenly spaced. So this means that as we look at how electrons exist in the atoms, we need to understand that they'll be in whatever the lowest energy orbitals are, right? So however many orbitals we have, we're going to start with our lowest orbital, and we're going to start filling our orbitals with electrons in a way that makes sense for the atom to fill. And so that means we need to get back to our quantum numbers and see how the spin quantum number actually affects how we fit those electrons into the orbitals. So we haven't really talked very much about the spin quantum number. I introduced it and then we kind of ignored it for a while. So our spin quantum number let's actually look at all of our quantum numbers again. So we have our 1s orbital, and this has n is equal to 1, L is equal to 0, m sub L is equal to 0, and we have two possible m sub s values, plus 1/2 and minus 1/2, and this is true for every single orbital. And a while ago I mentioned that each electron needs to have a unique set of quantum numbers. At least one of them needs to be different inside the atom. And this is how the spin quantum number actually helps us out, because that tells us that for the 1s orbital, we can have one electron that has the quantum numbers 1, 0, 0 plus 1/2. That's one electron. And then a second electron that can also be in the 1s orbital, but it has minus 1/2 as its other, as its fourth combination of numbers. And so even though these three numbers are the same, because the spin number is different, now these two electrons can be in the same orbital. And so typically when we talk about spin up electrons, that's what this positive is called. This is called spin up. We represent it with an up arrow, and this negative 1/2 is called spin down, and we represent it with a little down half arrow. And so typically these are paired up together in an orbital like this. Sometimes we will also put it in a box, and we will usually label it either way with what kind of orbital it is, 1s in this case. So now we can reconnect with the elements. When we look at elements, we've already said we know that hydrogen has one electron. And if it's going to be in the ground state, the lowest energy state possible, it is the 1s orbital that is the lowest energy. And so we would write its electron configuration either as up, down, oops, excuse me, that would be 2 electrons. We will either have a little line for 1s, or we will say, here's my 1s box, and I'll have 1 electron. By default, we put the electron as spin up. So if we have an unpaired electron, or more than one unpaired electron, they will be spin up. And that's, it turns out to be a slightly lower energy configuration than having it spin down, and so that's why it's spin up. Okay, so if we have multiple electrons now, like if we have helium, that's 2 electrons, right? It has 2 protons, 2 neutrons, 2 electrons. So we're still going to have 1s orbitals, and we're going to have 2 of them. So we would have up, down for our 1s, or in our little orbital box. But more commonly than the orbital box diagram, we'll actually show an electron configuration for any element as the orbital, and then how many electrons are in it will be a little superscript off to the right. So we would do that for helium as well, 1s2. And this is how we would say it, 1s1, 1s2. That would be how we speak the electron configurations. So let's take a quick look at figure 730 from our book, because this gives us a few more electron configurations to look at. This figure shows the orbital diagram, so the orbital box diagram, for the first 10 elements. It also shows the electron configuration, which I just barely was telling you about. And then we have an abbreviated configuration as well that I'm going to mention in just a moment. Now, what's good about the orbital diagrams is that it gives us a visual display of how these orbitals are being filled up. So when you have partial filling happening with, for example, these 2p orbitals, you can see that they are filling up with not being paired up first. So these ones are all unpaired, and then we start pairing when we have to. And that's generally true since electrons repel each other, they're both negatively charged. We're going to find that electrons prefer to be unpaired most of the time if possible. And then if they have to have a partner, then they will. But you know, we're going to have some trends that we discover here. With the electron configuration, this is a little bit more condensed, but you know, condensed compared to this orbital diagram. But it's still fairly lengthy. For example, what if we had to do the electron configuration for a really big element? Let's actually take a moment here and let's practice doing an electron configuration for a slightly bigger atom. Let's go ahead and do magnesium. So practice here with magnesium. So first you need to take a second and look at the periodic table and figure out how many electrons magnesium has. So pause the video and go take a look at your periodic table and then come back. All right, hopefully you saw where magnesium was and identified that it has 12 electrons. So when we write our electron configuration, we're going to start filling from the 1s orbital, and then we're going to keep filling on up. So we can fit 2 electrons in the 1s orbital, and then we have a 2s that comes next, and that will fit 2, so we have a total of 4. So maybe I'll keep track over here. And then we have a 2p, and so 2p can fit a total of 6. So now I'm up to 10. And after 2p, we get to 3s, and I have 2 more electrons that are going to take us up to that total of 12. So this is our electron configuration for magnesium. So now remember that helium had an electron configuration of 1s2, and neon had an electron configuration of 1s2, 2s2, 2p6. So let's take a moment and remember what that's looking like in terms of our shells, right? We have the n equals 1 shell, which just contains the 1s. So this is a full n equals 1 shell. For n equals 2, we have 2s, and we have 2p, and there's 3 orbitals in the 2p's, right? It's going to be awkward regardless of how I wrote that. I'll fix it. There we go. So now this also has, for neon, a full N equals 2 shell. And what do we know about noble gases? We know that these are not reactive. So it looks like this not reactive characteristic must be related to full electron shells. And that does turn out to be the case. So when we write electron configurations, this one wasn't too bad, but just imagine if we were going to do like barium or something instead. Take a look at barium on the periodic table. The complete electron configuration for barium would be really long. So instead, we use the noble gas electron configurations. We say, what was the noble gas that came right before this element? In this case, it was neon, and so we write neon's elemental symbol with brackets, and then we just write whatever's left over. So this would be the condensed or abbreviated electron configuration for magnesium. For barium, if you look at the periodic table, you can see that the noble gas that comes right before it is xenon. And now we can count down on the side of the periodic table and see that we are at the n equals 6 row, and so we have 6s2. So this is much better than having to write out that complete electron configuration. Now, I hope that you are starting to recognize a couple of things about the shapes of the periodic table. Notice that this first set of columns here, this is 2 elements wide. And our middle, those transition metals, this is 10 elements wide. The next one over is 6 elements wide. And then that little offset down below is 14 elements wide. Notice these numbers and think about the s orbitals and how we can fit 2 electrons. The p orbitals and how we can fit 6 electrons. The d orbitals and how we can fit 10 electrons. And the f orbitals and how these can fit 14 electrons. This is exactly why the periodic table is organized this way. It is because these elements have their highest energy electrons are in each of these orbitals, or these types of orbitals. And where those electrons are organized into orbitals affects a lot of their properties, which we're going to get into a little bit later on. So this is why we sometimes call this the S block, the D block, the P block, and the F block. Hopefully this is all starting to make a lot of sense. Now, some people will spend a lot of time talking about electron configurations. Early on in the periodic table, we have a pretty organized way of looking at those electron configurations. So let's go back really quick over here, where we start with 1s, 2s, 2p, and then 3s, and then 3p, 4s. But things start to get kind of disorganized pretty quickly. So there's not a lot of purpose in worrying too much about some of the really later on exceptions to the rules. We're just going to go through the first row of transition metals where there are 2 exceptions to our kind of quote-unquote rule for how things get organized into those orbitals. And otherwise, we are not really going to worry about some of the crazy electron configurations that come later on. The important thing that I want you to learn about the electron configurations is more about how many electrons are paired or unpaired in that highest level. So the other thing that we want to talk about here in terms of terminology is that when we have something like that magnesium, which I'll rewrite, 1s2, 2s2, 2p6, 3s2, or in other words, neon 3s2. We're going to have two terms here. These are going to be called the core electrons, and these are going to be called the valence electrons. And these core electrons, they are mostly not doing anything. We'll just say inactive. And these valence electrons are where the bonding happens. So it can be pretty important to be able to distinguish how many core electrons something has and how many valence electrons something has. So look for that noble gas configuration to help you find the core electrons, and then everybody who's left over is going to be the valence electrons. So I think that's enough for right now, and then we'll come back with some additional content in the next one.